Hello! Last time, we heard about how IPv6 Enhanced emerged. Today, we're going to ask Robin to help us look a little deeper into what IPv6 Enhanced involves. Robin, what does the technology cover?
Last time, I briefly talked about IPv6-based protocol innovations such as SRv6, network slicing, in-band flow measurement, BeerV6, and APN6. In practice, IPv6 Enhanced also includes technological innovations such as network analysis, automatic optimization, and network intelligence, as well as business model innovations that help drive diverse industries toward the digital era.
How do you define the technological innovations you refer to?
IPv6 Enhanced is a protocol innovation based on IPv6, and protocol innovations are the basis of IPv6 Enhanced's innovations. However, innovative technologies based on IPv6 Enhanced are actually a wider project, involving more than just IPv6 extension in the forwarding plane. In fact, many other technologies are also required to form a system so that IPv6 Enhanced can work better. In-band flow measurement is a good example. In the past, we used to monitor IP traffic out of band. Service packets were transmitted along a path with dedicated OAM packets then sent to measure the performance of that path. However, because load balancing is common on IP networks, it was possible that even though the destination addresses were the same, the service and OAM packets were transmitted through separate paths, resulting in incorrect measurement. In contrast, in-band flow measurement allows monitoring information to be directly carried in service packets, making it possible to perform measurement based on real service packets. So this technology solves that problem of OAM packets and actual service packets being transmitted along different paths. However, in-band flow measurement also posed a challenge that we were unaware of when we started to develop the technology. We thought that adding measurement information through the IPv6 extension header would be sufficient. However, we also need to analyze this measurement information in order to discover network problems. Networks used to operate at tens of megabits per second, then at several gigabits per second, and now at 400 or even 800 gigabits per second. Imagine that the forwarding rate of an outbound interface is 800 gigabits per second, with each packet carrying flow measurement information. These packets need to be reported to the analyzer, and the traffic to it will likely reach hundreds of gigabits per second. All of it needs to be processed. Essentially, it would be impossible to process so much traffic manually, and so it became clear that the IPv6 Enhanced extension alone would not be enough for in-band flow measurement. We needed to implement automatic analysis by introducing big data analytics, intelligent analysis, and other technologies to enable the entire system to run properly. This is the only way to truly achieve in-band flow measurement. And, although big data analytics and intelligent technologies are not directly extended based on IPv6, they are an inseparable part of IPv6 Enhanced. These technologies can be regarded as enablers of IPv6 Enhanced protocol innovations and can bring IPv6 Enhanced into full play. Therefore, we define these technologies as technological innovations.
And what about business model innovations?
Last time, we talked about how applications promote technological development. At the same time, new technologies also foster new business models, forming a closed-loop process. In other words, we use new applications and new business models to drive the developments of IPv6. In fact, many new business models emerged during the innovation of IPv6 Enhanced technologies and protocols. For example, we've already said that 5G has changed the attributes of connections and that the cloud has changed the scope of connections. With IPv6 Enhanced technologies, network connections can be established more effectively and new services can be developed. A typical example is SRv6-based interdomain cloud private lines. Private line services can be easily deployed to meet the requirements of service cloudification, in turn generating a new business model. Another example is network slicing, which is now very popular. It better isolates services and guarantees resources, especially for 2B services, something that is very important for many enterprises. So, network slicing also creates new business models, which in turn promotes fresh innovations in protocols and technology, forming a virtuous cycle.
Some experts have pointed out that IP networks should be subject to ongoing improvements from 6 dimensions: automation, security, ultra-high bandwidth, ubiquitous connectivity, low latency, and deterministic quality. While automation, security, and ultra-high bandwidth are fairly easy to understand, ubiquitous connectivity is a little more unclear. What does it mean, and what service requirements does it involve?
Ubiquitous connectivity has 2 meanings. First, it means that there are a large number of connections. In the past, there were only a limited number of devices. Now, with the cloud, network devices can easily be built on it. So, we need a large number of connections for all of these network devices. Plus, as IoT develops, it's being deployed on more and more industrial campuses, driving even more devices to connect to the network. But ubiquitous connectivity also means that the range of connections is wide. Connections need to be set up spanning multiple network domains. And in order to avoid the management and maintenance difficulties that result from large-scale networks, a network must be divided into multiple domains. Now, traditionally, MPLS was used for interdomain connection, but that's complex. In contrast, interdomain connection using IPv6 is far more convenient.
And what about low latency?
Low latency is important for applications in telemedicine, securities, and education, for example, when transmitting information on the network.
What about deterministic quality?
Deterministic quality is special. Let's think about industrial manufacturing as an example. Here, large jitter is unacceptable. Once jitter occurs, an accident or problem with product precision may occur. So, there are strict latency and jitter requirements. And in the electric power industry, power differential protection also requires deterministic quality. Both latency and jitter must be controlled within a required range. This is what we mean by deterministic quality.
Deterministic quality and low latency are often used together. What are the differences between them? Could you give us an example?
Many people have asked this question. Because low latency is also involved in deterministic quality, confusion often occurs. Low latency focuses on the latency parameter. In most cases, deterministic latency may not be the lowest, but there will be very high requirements on jitter. For example, we often use planes, trains, and cars for transportation. We assume that planes are the fastest. That is, they have the lowest latency. But the problem with planes is that they are likely to be late through delays. And while flying by plane itself is fast, you also have to spend time getting to the airport, and waiting for the plane is frustrating. This is an example of low latency. Deterministic quality is similar to a high-speed train, which may not be as fast as a plane but is fast enough. In addition, a high-speed train usually arrives at the station at a specified time, give or take a few minutes. Think about the difference between low latency and deterministic quality like this.
You've explained the service driving force behind IPv6 Enhanced, but are the 6 dimensions you also referred to sufficient? Can they empower different industries? And will there be any supplement in the future?
The 6 dimensions currently defined for IPv6 Enhanced are based on new service applications such as 5G and the cloud. These dimensions are determined to better guide the development of IPv6 Enhanced technologies and the industry. In general, these dimensions match current 5G and cloud service requirements. But as I mentioned previously, IPv6 Enhanced is an open system. With the development of more service requirements and network technologies, the dimensions may change in the future. For example, in future network innovations, energy saving will become more and more critical. Dimensions related to it may then be introduced.
Thank you, Robin, and thank you for watching.